Hey, this is Jim Bergman with Imperial Tools. I want to show you a new feature we put in the iManifold application called our stability indicator. And the stability indicator is simply in there so that when you're servicing a system, adding and removing a charge, evaluating airflow, evaluating system performance, that you make sure you're capturing the data at the right time. So what we're going to show you is how the stability indicator works, walk you through a little bit on our application, just what the system's doing, explain how it's operating, and show you how things stabilize and what we're watching to make sure the system is stable. So we're going to go ahead and start the system up, and we'll watch things go for a few minutes, and I'll walk you through the process. All right, so you can see we have the system stabilized. A couple of things just to notice of interest is that we have 0.1 degrees of superheat and no subcooling. And our reason we have no subcooling is our liquid line temperature is 79.2 degrees, and we're at 78 on the saturation temp. So everything's pretty well consistent right now. What we're going to do is I'm going to go ahead and start the system up, and what I want you to pay particular attention to is how quickly that we reach target zones for the low pressure, the high pressure, the superheat, the subcooling, and airflow. Because when we reach that stabilization point on those values, you would think the system's stable, but I'm going to show you that it's really not. So we're going to go ahead and make sure the gauge, everything's ready to go here. So give me just 1 second. We'll go ahead and start the system up and cooling. And by the way, here we'll just flip to this just so you can see this here on our probes. So we have a ½ degree split right now, which is probably just the difference between the two sensors themselves. We're not doing any cooling. Here's our target suction pressure, superheat, subcooling, and high pressure. Our air side measurements, return air wet bulbs and dry bulbs, supply air wet bulbs and dry bulbs, and back to our active temperatures on the gauge set. So we're going to go ahead and start the cooling up. So right now you can see the stability indicator in the top left-hand corner, and it is showing that the system is stable, and now it just went to destabilize because it was stable a few seconds ago. Everything was sitting there idle, and now that we're starting up, you'll see the pressures are very quickly coming into range, which is pretty interesting how fast low and high pressure hit their targets. I mean, it literally took seconds for those things to hit their targets. Our TXV, you can see, is hunting a little bit. It went from up and down. We're now at 2.63 degrees superheat. Our subcooling is very quickly coming into range here. So we'll give this thing a few minutes, just sort of watch what's happening, and look at the trends as this goes. Now you can see on the bottom here, we are graphing temperature split, and our temperature split is continuing to increase. Our liquid line temp went up a little bit and is starting to stabilize. If we tap on the stabilization button, you can see right now, in fact, our liquid just went stable, and our temperature split still is not stabilized. So we'll give it a few minutes to run, and we'll see how this thing goes. Now what you're going to notice is really how long it takes for the system to reach a stabilization point. Now if we scroll through here, so we see BTUs. This is a 36,000 BTU unit, and it's showing it's doing 39,000 BTUs of cooling. Now that is because it's likely showing a high airflow. I'm just going to go over here to our performance for a minute. You can see our estimated airflow calculation is 482 SCFM, and it's dropping down to 469, down to 465, and it'll continue to drop down as the temperature split gets closer and closer to the target. Now this isn't a problem with our application. It is simply the way that this system is working. Until the temperature split is stabilized, you can't evaluate performance of the system. You can't do it. It doesn't matter at that point. Superheat doesn't matter, subcooling doesn't matter, nothing matters until the system is completely stabilized, and the way that it gets stabilized is through temperature split. So we'll give this a few more minutes, and eventually here we're going to see this coming into range. You can see we're coming into the range in the blue here, and in a few more seconds here we'll see our temperature split go to stable. So right now you can see also that there's no problems with the system, and if you were to take a snapshot at this point, you're still too early to evaluate the system performance. Our TXV is still hunting a little bit. That may flag again in the troubleshooting. We may miss that. We only evaluate system performance every few seconds. You can see that temperature split starting to flatten out a little bit. Again, if we tap on the stabilization key, you'll see the liquid line is stable, but the temperature split is not. And right now, that was at 1519, and we're about 1523 right now, so it's taken a few minutes to operate to get this thing to reach its total capacity. As long as that temperature split is on an upward trend, it's not going to stabilize, and right there you can see it pretty well flattened out, and the system now is considered stable. Now we're going to wait a few minutes, make sure it stays stable, but right now we're just above the nominal capacity of the system. We're at 3.1 tons, 37,000 BTUs. You can see it went destabilized for a second again, so we're going to give that a few more seconds here and make sure it stays stable. Well, once it stays stable, we're good to take a snapshot of the system performance. And probably right about here, it will stay stable. You know, if we watch it just for a little bit longer, we'll see that for sure. But now it's stabilized, and we could probably take a snapshot of the system performance. So this is the point now where we're stable. We go into our projects reporting. We take our test in snapshot, continue. And now we got a test and snapshot. We can make any adjustments that we have to make and evaluate the system operation. The reason we're looking at both liquid line and temperature split is if you add refrigerant to the system, the liquid line temperature will destabilize. What's going to happen is that refrigerant's going to have to get down to the condensing temperature. We add gas into the low side of the compressor. It works its way into the condenser, and then it'll stabilize in temperature in the condenser, and that may or may not affect temperature split. So temperature split looks at the evaporator side of the system. So what we're looking at is we're looking at the high side and the low side at the same time, verifying both sides of the system are stable, and then we're able to assess true equipment performance. So this gives you an idea of how all that works. Again, we'll go back into performance for just a second here. We can see our airflow now is down to 373 SCFM per ton. So it's within range of what's allowable. We're at about 400 ACFM per ton. So this thing's pretty well spot on. And if we're evaluating its performance, we're really quite good to go. So hopefully this gives you an idea about how that stability indicator works. And hopefully now you realize it does take a few minutes for the system to stabilize and to make sure that we have satisfactory operation. And this feature will really help you get good test in, test out results consistently every time. So just thought we'd show you this because it's just a pretty cool trend right here. We got a system that's stabilized. You can see everything's stable, and this is a perfect example of hysteresis in a TXV. In other words, the difference between when a TXV opens and the TXV closes. And you can see right here, when you look at this graph, that a TXV has an allowable swing of about 5 degrees, and this TXV is using every bit of that operating on this system. We're at 90 points of data, so you can sort of see the way things are going. And every time the superheat drops too low, the TXV closes. And when the TXV closes, the superheat starts to increase till it gets too high, and then the TXV starts to open again until it hits its low point and its high point, and it just keeps going through this cycle over and over. Now this is a perfect example of a TXV controlling. It's modulating. It's not what we would call hunting. We have a hunting TXV. That means that it's going down to 0 or very close to 0, and it can't control anymore. This TXV is modulating open and close, but it's perfectly fine, and it's staying within the allowable tolerance of the what we consider normal operation. But it's just really cool to see this. And you can see down here our subcooling is like spot on, dead constant. It's not moving a bit. It's just that small amount of refrigerant as the TXV opens and closes, making the superheat go from about a low of 4 degrees up to about a high of maybe about 13 degrees, and then it'll drop back down again. So just thought you might like to see this. It's not something we get to see all the time, and it was just a perfect set of conditions to capture this, and thought it'd be neat for you guys to see. 3-ton unit doing almost exactly 3 tons of cooling at a 20-degree split at about 11 EER, and this is an example of how a system should look when it's operating properly with the iManifold. Airflow in the middle, subcooling in the middle, superheat in the middle. And thing to notice here, by the way, just to point it out here, as long as that indicator stays within that yellow band, it's okay. The center band's ±3, the outer band is ±5, and while we see the TXV modulating in there, it's not going back down to 0, so it's not a problem. It's doing what it's supposed to do, and just really really cool to see this thing go through these cycles and watch it perform the way that we'd expect it to. So this is Jim Bergman for Imperial Tools. Thanks a lot for watching.